Okay, so in the last video we looked at this problem, and I'll just sum it up quickly. But in this video I'm going to say that we're going to extend the problem by predicting and relating these things algebraically. So what are the things that we're looking at? Well, in the first problem we're looking at these medalists standing on podiums, right? Here we have one medalist standing on one box, and the problem's saying, okay, you have that, well, what happens when there's two medalists? Well, you'd have two medalists. Here's the first one, let's say standing on the one box. The second medalist would then stand on two boxes here, higher, because they won. If there were three medalists, right, then you'd have three people standing on the podium, and you'd have 6 boxes in total. So we're looking at the relationship between the number of medalists, right, and and how that relates to the number of boxes we would need to hold them. So it's medalists, we'll call that x, the independent variable, and the number of boxes, y, the dependent variable. So we're trying to think, how do these two things relate to each other for any number of medalists? When you're doing something like this and you're given a visual, it might be a good idea to use the visual to understand what's happening. I would skip over the first scenario, right? One medalist in one box is not going to be very helpful, but here, two medalists in 3 boxes, what stands out to me right away is that we could think of this almost as a square, right? Now this square, what it would have is the 4 boxes inside it, if we had a real square. So my first thought was, oh, okay, I know we have 3 boxes. A 2 by 2 square would have 4 boxes. So maybe the formula is take the number of medalists, in this case 2, which would be x, and square it. So x squared, and then subtract, in this case, 1. So our working formula so far is x squared minus 1, except we want to keep testing it to see if it works in every case. In the next case, it wouldn't work because we have 3 medalists with 6 boxes, and this time in our grid we'd have to subtract, right, 3 empty spaces, not 1. But what you might notice now is, okay, well, here, if we have 3 medalists, right, maybe we're subtracting 3 boxes, and 2 medalists we're subtracting 1 box. So we can't just generalize in this way, x squared minus 1. It's not really going to help us. So then what do we do, right? What would work? Well, this is, I think, the fun part, and I feel like I'm partial to this because it's something I recognize and it's something I'm used to trying to do. If this shape doesn't work, try and create a shape that does. And what I'm going to do is, instead of writing or drawing boxes, if it takes too long, I'm going to represent them with dots. Right, so here, in the first case, with 1 medalist, we have 1 dot. With 2 medalists, we have 1, 2, 3 dots. Think of them as the boxes. With 3 medalists, we have 1, 2, 3, 4, 5, 6 boxes. And we'll just set up the 4th one as well. 1, 2, 3, 4. All right. In total now we have 10 boxes. Right? 4 plus 3 plus 2 plus 1. And we want to try and redraw the shape. Squares weren't working. Let's try rectangles. How am I going to build the rectangles? Well, all I'm going to do is basically repeat or copy the amount of dots we have and line them up so it forms a rectangle. And here, these 3 dots, imagine I piled them up, right? Same exact number of dots, but in the reverse order, so it makes a rectangle. And here, with 3 medalists, what would we have? Well, if we just copied that, really, it would fill this space up, right? And make another rectangle. And with 4 medalists, oops, move this, what would happen? Well, with the 4 medalists, the same idea applies here. We just kind of copy this thing and turn it around 180 degrees, and what we get is another rectangle. So it seems, at least even before we analyze this, that we can create these rectangles in every single case, right? So here it's working as well. So now, if the shape itself is working every single time, and here it would as well, by the way, just be a little rectangle like that, if you're able to make the same shape every time, that kind of gives a hint that you can probably make the same equation every time that kind of matches up. So we'll line these all up. So we have them at our disposal here. And I think we're now ready to finish. What are these rectangles really? Well, I'll start the second case again. For 2 people, what do we get as a rectangle? Well, for 2 people, we get a 2, right, by 3 rectangle. Okay, so this forms 2 by 3. For 3, we get what? Well, the height's now 3, and the width is 4. So for 2, we got a 2 by 3. So that number for 2 people, it's 2 by 3. For 3 people, it would be a 3 by 4 rectangle. And for 4 people, what would it be? Well, it would be 4, the height, by 5. So 4 by 5. So you can imagine, oh, and for 1, look at this one next, we have a 1 by 2. So now we have a pattern to look at here in the dimensions of the rectangle. For 1, it's 1 by 4. For 2, it's 2 by 3. For 3, it's 3 by 4. And for 4, it's 4 by 5. In other words, for the number of people we have, no, sorry, this is not 1 by 4 in the first one. What am I saying? It's 1 by 2. Fix that. Right? So now, I think if I write this correctly, we'll be able to see the pattern. Okay. For any number of people, for x people, let's say we had an x grid, there is x, right, times x plus 1 in total to form these rectangles, right? So cancel those out. So for here, right, for 2, it's 2, right, times 2 plus 1. And it's 3 times 3 plus 1, or 4. And 4 times 4 plus 1, and so forth. So for x medalists, how many boxes will there be? Well, y is always going to be equal to, in this case, so far, x, right, times x plus 1 in parentheses. But that's the full rectangle, and if these rectangles aren't the number of boxes, what are they? Well, these rectangles always represent double the number of boxes you need. If you look at each diagram, right, the purple dots represent the boxes that we actually have. But the purple and teal dots, all of the dots, represent double the number of boxes we have. So if this equation gives us the rectangle for double the number of boxes, we want half the number of boxes. How do you find a half? Well, you take the rectangle and then divide it by 2. So our equation is this right here. We can simplify it though. X times x is x squared plus x times 1, or x, right, over 2. And this is a quadratic equation. It's not linear. The rate of change here is always changing. So we can apply this formula if we go back to our table, right? We notice it goes up by 2, and up by 3, up by 4. For 5 boxes, it would be 15. For 6 boxes, right, we go by 6, so it's 21. Then we go up by 7, or 28. And we go up by 8, or 36. Let's see if this formula predicts the 8th step. So how would we do that? Well, 8 represents x, and we should get 36 for y. So we said y equals x squared. X is 8. So 64 plus x plus 8 divided by 2. That should give us 36. Does it? Well, yes, right? 64 plus 8 is 72. Divided by 2 is 36, the number of boxes. This equation relates the number of boxes and medalists. For all numbers of medalists. It's quite powerful. The next problem, this one they ran a carpet over the boxes, and this one was linear because we had 10 feet of carpet here, and then we just add carpet on each individual, let's say, podium or box in this case. So if there's one step, it's 10 plus 3, or 10 plus 1 plus 2, or 13 feet of carpet. And then for 2 boxes, even though we had 2 more boxes, we really only have 1 more surface to cover, the top part right here, another 3 feet. So it was 16, and then another 3 feet, and then so forth. So for each step, we had 3 more feet, right? 25, 28. Now this is called a linear pattern or linear equation because the rate of change is constant. Now rate of change is equal to slope. So we know that m equals 3. And that just means 3 for every 1, right? It's a delta y over delta x. Delta y means your change in y. Delta x means your change in x. And the number of steps here are the x. It's not the dependent variable here because the number of steps determines the amount of carpet you need. So delta y means change in y, or change in carpet length is 3 for every 1 step, delta x. And that's our rate of change. Now, all I have to think about now is, oh, well, if we had 0 steps, how many feet of carpet would we have? Well, I guess you could say 0 feet of carpet on one hand, because why would you be running carpet if there were no steps? But we want to look at this problem in the sense that there's always 10 feet of carpet, regardless of the number of feet of steps, or number of steps. So even if x equals 0, we still need 10 feet of carpet, right? 10 feet of carpet is always going to be ran regardless. So that tells me that, oh, if our general form of an equation is y equals mx plus b for a linear function, and when x is 0, that kind of cancels this term out. 0 times anything is 0. The b term, the y-intercept, is 10 or 10 feet of carpet. So our equation now we can just kind of plug in 3x plus 10. And it's our nice linear equation for this table. And you could try it. I mean, plug 8 in, for example. Here, if you plugged 8 in, you get 3 times 8, right, 24, plus 10, 34, which is the correct amount of carpet for any given number of podiums. Alright, hope this helped.